Oh, there we go. Let me make sure that I'm actually here. I am. Look at that. Howdy, everybody. I hope you're having an absolutely lovely day. I know I am, and it's only going to get better in a few minutes here. My name is Tim Sylvia. I'm an editor with PV Magazine USA, and I'll be your moderator for today's webinar, Revolutionizing Tracker Resiliency with Vanguard 1P. Joining me today are a host of excellent presenters, Gonzalo de la Vina, head of Trina Solar Europe, Oscar Aria, head of Solar Solutions for Trina Solar EMEA, Juanma Gomez Garcia, head of Support Structures Research and Development at TrinaTracker, and Dr. Jubair Chowdhury, a senior engineer with CPP. Before we hop into the presentation, we have a bit of housekeeping to take care of. This webinar will consist of a brief presentation with Q&A at the end, though you're free to submit questions at any time during the presentation. Due to time constraints, we may not have time to address every single question, but we will certainly attempt to. If you've ever attended a PV Magazine webinar before, you may notice that the platform looks a bit different this time around. The webinar will still function the same way that others have, just with a different interface that allows for better interaction with you, the audience. If you have any technical difficulties during the webinar, try refreshing your web page. If problems persist, shoot us a message and we will work to resolve it. In addition to myself, my colleagues Beatriz and Frederica are waiting in the wings to assist with any difficulties. And now that the housekeeping is taken care of, let's switch our focus back to the topic at hand, Trina's all-new Vanguard 1P tracker. To achieve the most cost-efficient solar installation, all hardware aspects and components need to be carefully considered, with module and tracker arrangement being chief among these concerns. While historically limited by terrain and the effects of high wind on a tracker row, one in portrait, or as we'll probably be calling them for most of the webinar, 1P, tracker setups have been proven to deliver reliable projects with low levelized cost of electricity. In pursuit of unlocking the true potential of 1P and eliminating barriers to its utilization, TrinaTracker has developed Vanguard, a new 1P tracker solution designed to conquer the terrain it's installed on and the wind it will face. To better understand what went into the development of this new product and why Trina has been focusing on extending the terrain trackers can be installed on, I'll turn it over now to our presenters who will get started on their slide deck. Gonzalo, the floor is yours.
Thank you, Tim. And thank you, everybody, for participating on today's launch of the Vanguard 1P. I'm very pleased to be able to participate here. And I will start giving you a short introduction on Trina. So if you go to the next slide. Correct. I will give you a quick glimpse on TrinaTracker and Trina as a company. Then Oscar will talk about our new product, the reason why we're here today, the Vanguard 1P. Then Juanma about the activities in research and development, and Dr. Chowdhury on the tests that have been performed with our tracker. Next slide, please. Good. Everybody in the industry knows Trina. At least that's my impression. We've been around for 25 years. So we were founded in 1997. This year's the 25th anniversary. But everybody, when they hear the name Trina, they think about modules, and we're much more than modules. And this is why I'm glad now to show you what we're doing. So Trina is a global company that operates across the whole value chain. We do the modules, as you see here, Trina Solar. We also do the tracker. We do turnkey projects. We do the storage systems, and also we do cloud services, which is all located in Trina Internet of Things. The combination of a TrinaTracker and the module is what we call Trina Pro. So we are more than just a product provider, we're also becoming a solution provider. Next slide, please. Good, what you can see here on the slide is our bankability of Trina. Trina has a superb bankability, as most of you know from the last 6 years. We have been repeatedly reported to be 100% bankable by Bloomberg New Energy Finance. Next slide, please. We've gained more than 18 years experience deploying projects with trackers in more than 40 different countries across 5 different continents. Today, we are one of the top 5 players in the tracker industry, and we have more capacity. We have more than 5 gigawatts of production capacity that we own. Next slide. Also, from a technical side, we are 100% bankable, as you can see, and has been proven by the DNV reports. Today, and this is something that differentiates us a lot from competition, I would say, is that we're the only company in the market that counts with extensive R&D, not only for modules, but also for trackers. So the combination of both, this is what makes us very special. Our R&D team has developed state-of-the-art trackers with own patented components like the spherical bearing and the Trina clamp. We have developed intelligent algorithms like the SuperTrack and the Smart SCADA, and for easy efficiency and for O&M. So besides our own manufacturing, that, as I said before, is more than 7 gigawatts, we also have own laboratories and testing facilities right next to our factories. And our products are tested by global wind engineers and consultant leaders like CPP, that is represented today by Dr. Chaudhuri. Next slide, please. Good. So we have developed, as I said, the 3 trackers, the 3 products that we have here, the Vanguard 1P, the Vanguard 2P, and the Agile. This combined with intelligent applications to increase energy production and achieve smart operational and maintenance, the SuperTrack and the Trina Smart Cloud. And what is more, with dedicated specialized individual teams with consolidated expertise in all the company's areas, like pre-sales engineering, project management, commissioning, after sales, and O&M. Next slide. So what are we trying to achieve with this solution that we're introducing here? We're trying to solve your main worries, which is mostly the cost of the O&M, and to extend the operation of a plant, and of course, to control and ensure a high level of energy production. We can eliminate these concerns by offering preventive O&M, robot cleaning, ensuring quality control in the manufacturing of our trackers, offering applications like the Trina Smart Cloud, doing the wind tunnel test, and develop our SuperTrack algorithm. I mean, the aim of all these activities is clearly to reduce the BOS cost, the LCOE, and the O&M, and at the same time, to increase the energy yield of a plant. So I give now to Oscar.
Thank you, Gonzalo. Thank you so much. Thank you to all the audience for participating here. It's a pleasure for me to introduce you this amazing new product, Vanguard 1P. Not only because of the exceptional technical results as an innovative element and product, but also because it is the result of a very hard job of all a brilliant group of colleagues from several departments and for several last months. Okay, let's go. Next slide, please. Vanguard 1P is a tracker with a configuration of one single row. This tracker is capable to support the 3 strings with the small modules and 2 strings with our high power modules. The maximum length we can reach is 110 meters. And the relevant thing is that we are flexible not only to assembly our actual high power modules, but also the bigger ones that I'm sure that are coming. Okay, so this is the real design, not for now, but for the next future. Next slide, please. Here you can see the main components of the tracker. single line tracker. We are equipping this tracker with some of the features or elements that are classical in our other designs, like for instance the Trina clamp that allow you to be 2 times more efficient in the installation, or the spherical bearing design that allow you to have a height adjustability. I will give you more details later on. But at the same time, we are including innovations in this tracker. The most important one is the torque tube design. We are considering the rounded edge tube profile that allow us to reach long spans and, of course, high loads, and allow us to install this tracker in the better landscape that represents the focus of the design, which is the huge landscape, huge projects, and the bigger projects in the market. Okay. Another relevant innovation is the using of dual dampers that allow us to increase the system's damping and the performance against the wind. And of course, the most important thing that is directly related to the cost is the option to have a reduced number of piles per megawatt. This is something really interesting, and I will give you more details to you. Okay. Okay. Next slide, please. I'm going to talk about first the traditional innovations from the company. This spherical bearing is a patented solution. It's composed. We are comparing this with the traditional cylindrical bearing used by other competitors. We use this is a self-lubricating technical plastic. This is the black part you can see in the picture on the left. We tested the resistance to solar degradation with an accelerated life test of more than 15 years. And the most relevant improvements or features that we have with the installation of this spherical bearing is that avoids the need for calibration during the installation process, because increase the tolerances for the installation of the torque tube on the over the piles. This at the same time minimize the structural stress in the formation because you can install the torque tube and the pile even with higher tolerance, but with without increasing the stress, not in an abnormal way. Okay. And the third one is important because enables to increase the ramming tolerance, and directly you increase the percentage of ramming pillars, ramming piles. Why? Because when you have a soil that is more harder than expected, in some cases the pile can be out of tolerance after ramming. If you have higher tolerance to install the bearing, of course you are going to have, as a result, a valid ramming. And if you have not a spherical bearing like our spherical bearing, and the tolerance is not as high as our tolerance, you are not going to have a valid ramming, and you need to go to a predicted solution or other different solution. So you are increasing the percentage of ramming solution piles in the plant with this solution. This is directly impacting into the cost of the execution of the plant. On the right side, you have an animation. You can see and perfectly understand how this bearing works. You know, this is turning in 360 degrees, and this is allowing you to have a torque tube working properly, even with the really misalignment with the piles. Okay. At the same time, this is relevant because allow us to reduce the time for assembly this piece compared with the cylindrical one up to 15%. Okay. Again, this is a traditional solution, and I think this is a good forward to go deeper. Okay. Thank you. Please, next slide. This is one of the most important innovations, is the using of angle torque tubes. If we compare the angle torque tube 130 per 130 with the standard 120 millimeters not angle, just the square torque tube, we can see here just going to the numbers, that the bending resistance is increased by 12.4%. The torsion resistance has been increased by 29. This is really significant, 29.6%. And both improvements allow you to reduce the number of piles around 12% and go to longer trackers. This is relevant, and this toolkit has been designed specifically for this tracker that has been designed to be the best solution for a huge landscape. Okay, please, next slide. Another relevant innovation we introduce here is the dual damper system. Dual damper system allow you to shorten the time of tracker oscillation, so you prevent oscillation spree, improving the dynamic response, and of course increase the critical wind speed. So at the end of the day, on the right side, you can see the animations and how is the oscillation in the first animation without tracker and with tracker. You can see both animation are really different. So the summary is by using this dual damper, you increase the damping ratio, reduce the dynamic amplification factor, and at the end of the day, you have a high gust wind resistance in all directions. Okay, please, next slide. Again, tracker, it's are flexible structures even with frequencies higher than 1 Hz. That's supposed to be rigid, but it's relevant and important to check not only the usual structural verification with the static analysis, but also the aeroelastic analysis. And we work on that direction in all our products. And as part of our product development procedure that will be explained in detail by my colleague Juanma later on, we include the 3 main wind engineering tests that you can see here, the wind tunnel pressure model test that allow you to get the pressure coefficient definition, the 3D full aeroelastic test that is used to get the critical wind speed of the structure, considering the structure as flexible, and the on-site plug test that is carried out in our technological center, which allow you to get relevant dynamic parameters like frequency and damping. Okay, in this case, we collaborate with the company CPP, who is today one of the bigger wind engineering consulting firm in United States. And our partner, Jubaya, will go in detail and explain better than me all these parameters or all these tests. Okay, please. Next slide. Okay, this is the alarm strategy we include into the TCUs of the tracker. Every tracker has its own TCU, and we configure the alarm, different alarms according to the project. You can see here the usual ones that are coming from direct order from the TCU, like the stop position related to the low battery, or stop position related to the lack of communication, or even other alarms that are coming directly from the weather station, like the wind alarm and snow alarm. Maybe you are more familiar with the wind alarm. It's the most important alarm in this case. And at the same time, we have another 2 alarms, manual stow alarm and the hail stow that is significant in specific locations. At the end of the day, the idea here is that we are capable to configure different alarms for the TCU according to the project, establishing with the customer the preferences and establishing with the customer the strategy. Okay? Not a rigid stow position, different stow position we define together with customer in a tailor-made way, and with the project the better strategy in this case. Okay, so this is the introduction of how flexible can we be in terms of communication and control of the trackers. Okay, please, next slide. This is relevant if I'm talking about very large layouts, very large projects. It's relevant to consider that we are talking about, in some cases, in desert areas or areas where the soiling ratio is high. And this is really significant because you can have a lot of problems because of the soiling ratio. You can have problems regarding the loss of energy. I checked some values about 15% along a year as an average, or even if you are involved into a sandstorm, you can lose even 30% generation in a couple of hours. So this is important for us, and because of that, we integrated the design of the top 5 robot manufacturers in the world into our trackers. These robot manufacturers define the elements that they need to install, or we need to install together with them, in order to have a proper integration of the robot with the tracker, not only the mechanical parts, but also the communication parts, okay? So this is relevant, and this information can be available even in our Trina Cloud software that I will explain you later on. Okay, please, next slide. This is the Trina Smart Cloud. This software is really amazing because it's not only focused on the tracker control, monitoring, and definition of parameters. We can also include the other parameters coming from inverters, from stream boxes, the robots, as I told you before, the production of the plant. And at the end of the day, we are capable to collect all the information, put all this data together in the cloud by using a remote monitoring and control the plant, in this case, the trackers, or the rest of the elements, depending on the customer selection. And we have this information that allow us to make an analysis based on artificial intelligence, and based on our own self-learning algorithms. So the real situation is that the higher is the number of data we have into the system and the number of plants connected to the system, the better is the treatment of the data, the conclusions of our algorithms, and the predictions. I mean, the idea of this SCADA, this system, is to predict and make a better O&M, or preventive O&M prediction, in order to reduce the cost of the maintenance, and of course, reduce the levelized cost of energy, or in this case. Okay, next slide. Another relevant feature that I think is one of the most significant ones is the SuperTrack. Okay, SuperTrack is a software that allow us to improve the yield of the plant. And we developed our own algorithms that allow us to have a really better performance of the plant. The SuperTrack is composed by 2 modules. First one is the smart tracking that can improve generation power in highly diffuse irradiant conditions. This is for bifacial modules, and this module boosts the energy production at the middle of the day. You can see the hours between 11 to 4 p.m. is the most relevant moment when this module increase the energy yield, because we define with this algorithm the best position of every single tracker, by considering the direct irradiation, the diffuse irradiation, and even the reflected irradiation from one file to other, in order to have the maximum yield on this case. At the same time, we can put the best position and reduce the rotation of the tracker to effectively extend the service life of the motor and the tracker. So this is relevant, and of course, the most relevant value is the 2% uplift of the energy production. Okay. The second module is please go back to the previous. Exactly. The second module is the smart backtracking. This is relevant for the first hours of the day and the last hours of the day. And this is allowing you to consider what is the location of every tracker in the terrain, and allow you to avoid any shadows in between trackers, even considering the slopes, the difference in the slope between trackers, and all the elements that we can consider for these estimations. This is relevant when you have slopey plants, for instance, and you can uplift the production up to 6%. So this is very significant. And in this case, we are considering with both modules not the traditional 4 inputs that the astronomical algorithm used to make this tracking system. We are considering 12 parameters, not only 4. So this allows us, together with the development of our internal algorithms, to boost the production of the plant. Okay, please, next slide. Here you can see data coming from real plants, okay, that allow me to better explain this. So the smart tracking is more relevant when you have a complex topography. The smart tracking is relevant when you have a high diffuse irradiance ratio and when you have a high albedo. But the real situation is, if you check here on the right side, 1, 2, 3, 4, 5, 6, 7, 8, 9 plants, you can check that the gain with the smart tracking is moving around 2.3 to close to 6%, and the gain with the smart tracking is moving from 1%, around 1% to 2.3. So the summary of both modules that work together can reach a value of up to 8%, 8.1%. This is a really amazing value in gain. This is the gain in production along all the year, okay? So this is the real situation for a project when you are optimizing the capabilities of these modules. For instance, a project that have a high diffuse irradiance ratio, you have a lot of cloudy days, you have a complex topography like we have, for instance, in Europe, in many places. This is boosting the performance, okay? These modules, SuperTrack is boosting the performance of the plant. Okay, next slide, please. Here you can see on the right side, just in orange, the 4 parameters that used to be considered, but the astronomical standard algorithm, and the 12 parameters are these 4 plus the other 8 parameters you can see on the right side that are used by the SuperTrack to get the optimal tracking angle. Okay, this is completely different, and even in some cases we define that we can absorb or consent some shadow in the tracker or in a part of the module in order to get a higher production from the backside. So this is really amazing. Okay, it's completely different way to track the sun in order to boost the production of the plant. Okay, next slide, please. Finally, here you can see the different configurations we used to work with in this Vanguard 1P with our modules. These are the high power modules, 550, 600, and 670. On the right side, you can see the number of modules per tracker, which is respected 2 strings per tracker, 76, 68, and 64. But the main conclusion is that we design our tracker to perfectly work with our high power modules. This is the idea, and we are launching a state-of-the-art product to the state-of-the-art modules. Okay. Next slide. Let me summarize in a quick way what this Vanguard 1P new product represents. High reliability coming from the using of dual damper design, a stronger torque tube design, and collaboration with our partner CPP in order to do and check and analyze and do new tests and put new hypotheses related to the wind tunnel test. We are reaching a high O&M efficiency by including the main clean road solutions in the market, and by working with our Trina Smart Cloud solution that allows you to monitor not only the trackers but the rest of the components. It's something that is it's a decision of the customer. Okay. Third point is we enhance the adaptability To higher slope, we can reach 20% slopes in north-south direction and 15% slope in east-west direction with this tracker, and the inclusion of spherical bearing that allow you to reduce the percentage of, to increase the percentage of ramming and to reduce the time associated to the construction. Finally, we increase, most important one, amazing solution, high energy yield, by the compatibility with our high power modules and by using our new super track innovation, tracker technology. These are the most relevant features of this new product. Thank you so much. I will be really happy answering your questions. I think this is my last slide. Next slide, I think, is this one. Okay, so I give the presentation to my colleague Juanma. Thank you.
Okay. Hello, everybody. Thank you very much, Oscar, for the interesting information. In my case, I'm going to give you a very short introduction of work that the research and development team is doing for the development of the trackers. So, as mentioned, my name is Juanma Gomez. I'm the head of Support Structures Research and Development Center. I'm located in Spain. We have two centers for the development of the trackers for the development. One is located in the north of Spain, in Navarra, and the other is located in China. And we have a very strong and cohesive group, which is built up with a lot of field engineers, like it could be mechanical, electric, aerodynamic, and other specialties. And so we are all together creating several solutions for these trackers for the portfolio, which are all of them, as you can see here, focus on the reliability, on the cost reduction, power generation, and operation and maintenance. As some of the results from this group, from this innovation, we have some patents like the ones Oscar has mentioned, which is the spherical bearing, which is the Trina clamp. These two are very well known. The super track that my colleague Oscar has mentioned is a very interesting new development, which is very interesting in terms of gain of energy. So basically, probably you know our other two products, which are the Vanguard 2P and the Agile 1P. This is the historical development from our team. And, Vanguard 2P is a solution which is based on 2P trackers. It's a very innovative solution because it has been included in a multi-point linear drive, which is able to manage correctly the reliability of the tracker due to the instabilities of the wind. And on the other side, we have the Agile 1P that probably you also know. We have here the double row tracker. This tracker is focused on managing also this reliability, but we are also trying to improve some of the problems that we found in the past due to the force transmission in the systems, considering push-pull bars and levers. And we are also including some improvements, adding more reliability, more deviations from row to row that can be feasible with this new system. And the new Vanguard 1P is the new generation that Oscar has been explaining to you. This is covering new developments, new solutions, but it's also including some of the old developments we obtained with the Vanguard 2P and Agile 1P. Okay, this is basically the flow chart of the development we are following. This is a very, very simplified slide. But basically, everything starts when we receive some requests from customers or from the salespeople or from wherever, whoever in the company or out of the company. Then the first step we are doing is something like a preliminary 3D model or 2D model, some sketch that we use to analyze the solution. And from this, we start to do some calculations on forces. So the first thing we do is obtaining some Fem Analysis, which is used to obtain some information preliminary about the stress status of the solution and where we can reduce material and where we can add material. So when this first preliminary analysis is done, we go for the model optimization. And then we go for new model analysis in order to check that the new optimization is passing and just to obtain a cost reduction. So when this Fem analysis pass, we go to this part, the green part, which is very important because it's mandatory in our company. We are not stopping just in the calculations by finite element and modeling. We are also doing tests and joint validation because, as you could maybe know, in the calculations, when you are using this finite element modeling analysis, you have to, in some cases, take some assumptions. And maybe these assumptions will not be, in some cases, very similar to the real world. So we are testing everything apart from doing this calculation. Okay, so this is some of the pictures that we get from the development of our Vanguard 1P. So, sorry, as you can check in this first slide here in the bottom left, you can see that we start with the standards information for the calculation and with the tool that CPP is providing to us, which is the wind tunnel test information. So this is containing the coefficients or the instability velocities that we have to use in the development of these trackers. Then with this information, the first thing we are doing is just doing these calculations, as I mentioned before. You can see some of them here on the top right. So these parts help us to understand which is the real situation of these parts and which is the real stress and which is the possible failure of these parts, and try to improve it to avoid this in future, doing a reliable tracker. So from this point, where we go is to these intermediate photographs in the middle, which is each of these parts are tested. So all of them are tested mechanically and dynamically, doing a completely analysis of which is the deformation that we obtain of the test, which is the real performance of these parts under the forces that it has to be submitted. And at the end, what we do is we build also, in any case, the complete tracker. So we need to build a complete solution to analyze how all these parts are going to work together. These complete tests are serving us to, are used to obtain informations like consumptions, like loads, like instability in some cases. Like, well, we have to check that the complete solution, not only each of the parts, is working perfectly and according to the specifications. And even in this case, when we finish this test and we get the validation of the trackers, we still keep some other analysis, like it could be the CFD for specific locations where we can have, for example, different slope conditions or something similar. So as mentioned by Oscar, this is one of the most important parts from our current procedure. Maybe later, Yubaya from CPP will explain better, but I will give you some introduction information about this. So the first information we are obtaining from this starting point sketches and models that we do in the development is providing some 3D model, some drawings, to CPP, including some analysis, like model analysis that we use to find out which is the intrinsic vibration mode of our trackers in each case, like torsion and heaving. And also we are doing free vibration test. This free vibration test is done on a real prototype, which is built in our location, in our facilities. And what we do is we do this test just doing several procedures, like it could be video analysis, it could be also accelerometers, we could use lasers. And with this information, we obtain two different main informations from CPP, which are used by our engineering team to do the calculations that will help us later to analyze the loads. The first one is the rigid pressure test, in which we obtain the static coefficients and some dynamic amplification factors. And the second one is the full elastic test that we use to analyze the instability of our tracker. Okay, so here we can see two pictures of these tests. Okay, so the first one is this pressure test. So the pressure test is providing, as mentioned before, these coefficients we use to analyze the forces and the moments on the trackers. We can see here, for example, one curve, which is the dynamic amplification factor curve, which is containing for different damping factors the different dynamic amplification force according to the reduced frequency that we have on the tracker. And on the right, we can see the full elastic study. So we have the main result from this test is this critical speed curve, which can allow us to define which is the stall position, which is the maximum speed that our tracker can be able to withstand without these instabilities. And so this is a very important tool for our development. So we are not just stopping on the normal test. We are doing additional studies to analyze all the conditions that we can find in the facilities. And it could be larger tilts for 75 degrees. Here also we have some different exposure, like D terrain instead of the traditional C terrain. And also we are doing additional slopes, like a 15% slope. Okay, as mentioned before, one of important thing in our development is always the test. So we can see here that we do a lot of different tests. That you can see here, some of them, not all of them, because there are many we can include. But we are doing high load tests first of all. This is a test which is focused on obtaining which is the deformation, which is the maximum load that the system can withstand without breaks, without deformations, and so on. Then we have fatigue and dynamic tests. This is also very important nowadays. So normally the design somehow before it was done going to the yield point and see when we have plastic deformation. But the fatigue is very important, and dynamic test is important because we can have also some problems coming from the accumulated damage that can happen to a stress that are under the yield point. So we can calculate in this way how long our parts will survive. We can also do some additional tests like salt-strike fog tests or other tests. As mentioned, there are many more, but I don't have all of them here, obviously. And well, these are some other tests which are, in my opinion, very important for us, which is the whole assembly test. We have in our facility some areas to test our trackers completely before they are put on the market. So here we test the slope conditions, how the system is working with different slopes. We also test the consumption. We also are doing the test for the IEC accelerated test. And some other different things that you can only do on the field and not only in specific parts. And as mentioned, always an important test is doing operation test. That is including some things like the communication of the TCUs and CU and everything to be completely sure that our system is reliable enough to be installed on field without problems. So this is a very important point for our test. And as a result, for the work of the team of research and development, one of the important things is that we have more than 20 patents and utility models related to the tracker technologies in the market, and we are still working even in some more. So this is a very active part of the company, which has a lot of support and resources by Trina, and this is very important part of the design. So I think this is all from my side. So I leave our partner, Jubair. Thank you very much, everybody, for attending.
Thanks, Juanma and Trina team for inviting us to participate in this webinar. It has been a great pleasure working with Trina over the years. So at this point, I would like to take a step back and introduce CPP before moving on to our ground-mounted services and the work that we have done with Trina. So Dr. Jack Sarmak founded Sarmak Peterka and Associates in 1981 with Dr. John Peterka. And 3 years later, Dr. Ron Peterson came on board and formed the Sarmak Peterka and Peterson, the CPP as we know today. Here in this photo on your right, you can see Dr. Jack Sarmak on the right and Dr. Alan Davenport from Western University, Canada on the left with the famous Twin Tower model in the wind tunnel. An interesting fact, Dr. Sarmak and Dr. Davenport first came up with the term wind engineering, and it used to be known as industrial aerodynamics prior to that. So our headquarters in Windsor, Colorado is home of our 2 brand new state-of-the-art boundary layer wind tunnels. Our 3rd wind tunnel is in Sydney, Australia. We have offices all around the world. And with 40 years of experience and over 4,500 projects worldwide, CPP is the largest and most experienced wind engineering consulting firm in the US. So here we have on your right a 3D rendering of one of our wind tunnels here in Windsor, Colorado. For the purpose of scale, we also have rendering of people to give you a sense of the scale. And one of the unique features of these wind tunnels, also known as the boundary layer wind tunnels, is how we generate the atmospheric turbulence at model scale. So on your left, there is a photo of the upstream section of the wind tunnel. And you can see in this photo, we have these spires, which are the triangular shaped structures, light gray, kind of far in the photo. And then right behind the spires, we have this black solid plate, which is called trip. And then we also have hundreds of roughness elements on the tunnel floor, and the height of which can be adjusted. And the combination of all these three, we can generate atmospheric turbulence at any model scale, and also for different exposures or terrain types. So moving on to our solar services, CPP started looking into ground-mounted solar somewhere in the middle of 2000s. And after doing several projects, we realized that there are quite a few parameters that are somewhat similar across different systems. So then we started kind of building our own database. So at this point, we have tested hundreds of different configurations, kind of looking into different ground coverage ratios, different tracker height, different tilts, and different wind directions. Literally, we have collected like billions and billions of data points with these hundreds of different configurations at this point. One of our newest addition to the database is our topographic database. So now we can provide a recommendation on how to adjust the load coefficients when the trackers are placed on a hill or a topography. This database has been very popular among our clients because it can save a lot of time and money when it comes to a very generic tracker structure. Aside from the rigid model test or our rigid model database, we also provide services related to aeroelastic instability. So by aeroelastic instability, we don't mean that any type of deflection. Aeroelastic instability pertains to continuous kind of cyclic motion that grows into larger motion, or like a sudden motion that is tied to a specific peak-to-peak deflection, for example, 20-degree peak-to-peak deflection or 30-degree peak-to-peak deflections. So a couple of the services that we have for aeroelastic instability are the instability screening and full 3D aeroelastic wind tunnel test. With instability screening, we use analytical approach, sometimes CFD simulations, and also our past experience to come up with the instability wind speed or the critical wind speed. However, this type of study has a lot of conservatism built into the study because it has to make a lot of assumptions to it. On the other hand, the full 3D aeroelastic wind tunnel studies are the most realistic representation of the trackers in the field. Here is an example of what we get out of our rigid model study. So this particular example here, we have the wind coming from the southeast direction, so kind of the bottom right corner of your screen. So as you can see here, for this particular case, the trackers are facing west. So this is like an uplift condition. And as you can see here, the first row is getting hammered. So we have like higher pressures on the first row, and then we just kind of dropping towards the interior rows. And we also have like higher pressure coefficients kind of towards the corner of the trackers. So as you can see here, this is showing the fluctuating nature of the flow. And with this type of information, we can not only get the load coefficients for larger tributary areas, such as a tracker wing or a post tributary area, we can also get load coefficients for the smallest component of the structure, such as like a clips or clamps that's holding the modules to the rails. On the other hand, from the aeroelastic study, what we have here is like a couple of illustration of two of the most common torsional instability that we see. So before starting the video, I would like to explain a bit. So this is on the left, we have what we call the low tilt instability or the torsional divergence. First of all, these contours are obtained from 2D numerical simulation just only for the illustration purpose. And the contour here is showing the vorticity. So if you see bright red colors or the orange colors, that means the vorticity is forming and it's very strong. So for the low tilt instability on the left or the torsional divergence, what happens is the vortices are formed from the leading edge towards the upper and lower side of the panel, and the alteration of this, like alternating nature of these vortices kind of creates the instability. On the other hand, for the moderate or high tilt instability, what we call the vortex lock-in, we get the vortices shading off from the leading and trailing edge of the module, and again, the alternating nature of the shading of those vortices can create the unstable nature of the trackers. And if the tracker is moving for like a lot and kind of passing towards the horizontal tilt line, the vortex lock-in can turn into torsional divergence. Let's take a look at the torsional divergence videos now. So here you can see the vortex is forming at the leading edge, on the upper side, on the lower side, and it's making the trackers violently unstable. We can now take a look at the other instability, the vortex lock-in. So here you will see the vortices are forming on the leading and trailing edge of the panel and making the tracker unstable eventually. Moving on. So this is the type of curve that we usually get from a aeroelastic like full 3D aeroelastic wind tunnel study. So what we have here is the critical wind speed, or the wind speed at which the tracker goes unstable on the vertical axis, and the tilt on the horizontal axis. And we also have like two separate curves to show the effect of damping. So the blue curve, which is of the W shape, is for low damping system, where we have the wind speed decreases from 0° tilt, and then it raises back up at the higher tilt. On the other hand, for the high damping, where we have the effect of the damping on the moderate to high tilt, you can see that the wind speed, the critical wind speed, is increasing as we are moving away from the 0° tilt. So for Trina, we have performed static and dynamic analysis based on our database. And with this type of study, we were able to provide design load coefficient to kind of design different structural components of the Trina solar tracker system. And so in addition to doing tests on or looking at the results from flat topography, we have also provided adjustment factors for load coefficients for solar trackers on a hill or on a topography for Trina. We have also performed aeroelastic, full 3D aeroelastic wind tunnel test for Trina. So full 3D aeroelastic wind tunnel test has several advantages over section model testing. A couple of the advantages are like one, with full 3D aeroelastic test, we can look into the effect of cornering winds, and more often than not, we have seen that the cornering wind can dictate the critical wind speed compared to a head-on or straight wind. On the other hand, the second point is with full scale, like full 3D aeroelastic wind tunnel test, we can also take a look at the row-to-row interaction. In many cases, we have seen that the first row or the upwind perimeter row is moving very little, but that very little movement on the first perimeter row is cascading down towards the interior row, causing the instability at the interior rows. So here I have a couple of videos to show the effect of damping. So this first video shows the system without the damper. And as you can see here, the first row is becoming like violently unstable, and the motion is also cascading down towards inner rows. On the other hand, for the second video, this is with the system with high damping. And as you can barely see any movement because the system was stable up to the top tunnel speed. Moving on. So this is my last slide, probably the most important slide. So in this slide, I'm showing again the critical wind speed versus tilt that we obtained for Trina. So again, on the vertical axis, we have the critical wind speed. On the horizontal axis, we have the tilt. And all these crosses are kind of when each of the rows goes unstable. And the large gray band at the top of the plot is when the trackers did not go unstable at the top tunnel speed. As you can see, because this is for a high damping system, the bounding curve, which includes some safety factor, is of the U shape. Another thing to notice here is the positive tilts, which is leading edge nose up into the wind, versus the negative tilt, which is leading edge nose down into the wind. The positive tilts are usually less stable than the negative tilt. So this type of plot or information is very important because it gives us two very important key information. Like, first of all, it tells us when to be in stow and how much the tracker can withstand, how much of a wind the tracker can withstand during a design storm event. So with that, I would like to conclude my presentation. I would be happy to answer any questions you have. And over to you, Tim.
This is Friederike from the backend. As Tim is having currently some technical problems, I'm just going to invite all of our presenters to join us on stage. Please turn on your cameras, and we're going to get started. I'll throw the first questions at you. So hopefully Tim will have time to return. And there you are, Tim. I'm going to hand over to you.
Here I am indeed. Sorry about that. A couple quick technical difficulties there on my end, but we're going to get it started. We're going to go a little bit longer than our scheduled time here, just so we have time to ask a couple of questions from the audience. The first among those would be, what is the slope tolerance of the Vanguard 1P? It states that this is a terrain following tracker, so our asker was just kind of curious what part of the tracker allows it to be terrain following and what is the slope tolerance of it.
Okay, maybe I will give you the response about this information. So the tolerance is for east-west slopes is a 15%. I think Oscar also mentioned in the presentation, but for east-west is a 15%. For north-south is a 20%. So that would be the tolerance for this tracker.
Someone was asking about another of Trina's 1P offerings, that being the Agile 1P tracker. What is kind of the status of that tracker with regards to this new offering? Are they going to coexist? Will one phase out the other? Just kind of how the tracker ecosystem is going to work for 1P with this new offering. Hello? Did I lose you guys?
Sorry, Tim, I didn't catch you well. Sorry, can you repeat the
question?
Oh,
I'm sorry. Okay, yeah, my microphone must have cut out there briefly. Someone was asking what this means for the launch of Vanguard means for the Agile 1P tracker, if they will continue to coexist as products in their own specific usages, or if this will be a transition to Vanguard becoming the premier 1P solution for Trina.
Okay, yeah. Okay, mainly our as you know, we have a talk in our presentations that the company is very focused on customer requirements. So we are very very focused on providing the right response for the customers. So initially, we don't plan to retire any of the trackers. We still want to keep our agile tracker working, since the tracker is working good. Our development has been done in a proper way as the Vanguard 1P. The only difference is the two trackers are for different purposes. Okay, so normally, as you can see, for example, this Vanguard 1P is a long tracker that could be more installable in some locations, like it be these deserts or landscapes that are big landscapes, while the agile is something like a more shorter tracker that could be able to be installed in different locations with the more complex layouts.
Mm-hmm. Thank you for that. Juanma, I believe this next question here was for you, and it was just quickly asking, what are the basic advantages of dual dampers?
Okay. Well, I think this is related to what Jubair mentioned during the presentation. So the advantages that we can get with the dampers is basically that we are increasing the damping of the system, of the tracker. Okay, so increasing this damping on the tracker means that we are able to reduce the DAF, the dynamic amplification factors, which means that we can obtain a more cost-effective solution. And on the other side, we are also, let's say, increasing the values of our instability curves. We are allowed to obtain a better performance of the tracker against instability. Sorry. Okay, I don't know if my colleague Jubair wants to add something here, but more or less these are in my opinion, for the tracker, the main 2 points that can be affecting to the tracker.
No, you covered it pretty well, Juanma. So yeah, with higher damping, the dynamic amplification factor goes down. So that kind of helps towards the total loads of the system. And as you have seen in the video, damping can improve the instability wind speeds at moderate to high tilts.
Thank you, Jubair.
Another question here, I believe that will be for Juanma, is how does the Vanguard handle undulating terrain? And could you just kind of dive deeper into, how it would handle undulating terrain and, maybe sites that are uneven across the board? The whole of the site is on uneven terrain.
Well, this is a difficult question to respond in this case for Vanguard 1P. I mean, normally, one of the things that we are doing, one of the services that we include when we are analyzing some layouts is just basically this: analyze the layout and check which kind of installations we can do on site. So when we have uneven terrains, well, first of all, we have to know which kind of uneven terrains we are having. If this is a very soft uneven, maybe it's feasible to be installed. If not, we have to think in other solutions like the Vanguard 2P or the L1P. But it is difficult to say only if it's installable or not in uneven terrains. We have to analyze case by case.
Mm-hmm. A specific question coming in here on the SuperTrack algorithm, and our question asker was wondering if it can be implemented in simulation software such as PVSys to simulate its effects on a project's overall generation, or in trying to figure out potential hardware usages for a project. So can it be loaded into project simulation software?
Yeah, okay. One thing we are doing, yes, this is ongoing, okay? So what we are doing, our team has been analyzing some of the coefficients that we need to use or what need to adapt. Obviously, this is going to be affecting the algorithm that are used in PVSys, for example. So when we are using the PVSys, we need to, when we're doing the simulations, we are just doing the calculations according to the algorithm that is used in the software. So it is not so easy to install or to adapt this algorithm to the software, because the algorithm that the SuperTrack is using is different. Maybe one of the things is that, as mentioned by Oscar, this is a double problem. The first problem is that we need to take into account the different heights on the algorithm, which is installed in the smart backtracking. And the other point is that we have to use the smart tracking which is not always, let's say, that the position of the panels are more focused on different aspects that are not only one. Let's say we are taking into account many things like diffuse light reflections, light albedos, and so on. So it's not a fast thing to do to implement in simulations, but we're working on that.
Mm-hmm. Awesome. Thank you very much for that answer. And thank you all for your presentations and contributions to our webinar here today. I know I personally thought it was wildly insightful, and I thought it was great to kind of get a look behind what goes into the development of a new product like this. So one more time, I would like to thank you, Juanma, Gonzalo, Dr. Chaudhuri, everyone who presented today for joining us in our presentation. And before we go, I know we have a little bit of housekeeping here at the end as well, like we did in the beginning. So that should be showing up on your screen here shortly. Well, if it doesn't show up, I know the script anyway. We have some webinars coming up on PV Magazine, just like you tuned into here today. You can find those by going to www.pvmagazine.com/webinars. We have a series upcoming, and if you go to that page, you can also go back and re-listen to recordings of this webinar or any other webinar that we've had in the past. And you can also get a 10% code off of a subscription to PV Magazine Global with the code webinars 10. Here we go. It should be showing up here in just 1 second. And we also may be getting a preview for some articles that have been in recent editions of the print magazine. So if you like the sound of those headlines, feel free to apply that webinars 10 promo code and save 10% on your PV Magazine subscription. And it appears we're having a few more technical difficulties here loading what should be on your screen. So at this time, I would like to, there we go. I would like to thank our presenters one more time, and I would like to thank you, the audience, for joining in on this webinar. There will be a survey that you will be receiving shortly after we wrap up this webinar here. If you could fill that out for us, that would be wonderful. It helps us to develop content that is especially suited to what you, the audience member, wants to see, wants to learn about. And your feedback goes into the development of all of our future webinars, so your voice is heard. One more time, thank you very much to our presenters and our audience. I hope the rest of you have a wonderful day or evening, depending on where you are. Thank you.
Thank you.